So, let's continue on. Last time we introduced the first law for steady flow control volumes, both a general form. I'm going to write it quickly because we just, unless you took a break between lectures, you've just seen this. First law for steady flow. This is the general expression. So if I've got a steady flow control volume, again, chapter 5 is going to be first law for control volumes. Add the in, subtract the out. So if it's control volume, the way energy can come in can be a power input, it can be a heat input, and you can have mass at all of the inlets. Everywhere mass comes in, that mass is going to have enthalpy, kinetic energy in, and potential energy. Everywhere mass comes into the system. This is the energy of the mass in. Subtract all these terms out. The power output is W dot out. The heat rate out, Q dot out, minus the total for all of the outlets, the rate at which energy goes out through mass. That's the mass flow rate times the enthalpy plus the kinetic energy plus the potential energy. This is the energy of the mass in. This is the energy of the mass out. So this is add all the ins, subtract all the outs. That equals the change. If it's a steady flow control volume, at least in our text we call that steady flow, that's equal to 0. The change is 0. And we said if I've got a steady flow control volume with one inlet and one outlet, which is going to be pretty common. With one inlet, we'll call it 1, and one outlet, that's going to be at a different state, we'll call it 2. So if I've got a system where I've got mass coming in, mass going out, if it's steady flow, that means the change between the inlet and outlet is 0. So that means it's the same mass flow rate in and out. So again, add the ins. That's the power input plus the heat rate in. I'm going to group the mass together in one group. So I'm just going to have heat in plus work in. Yes, Izzy, we're recording. Thank you for checking. Minus the power out minus the heat rate out plus m dot times h1 minus h2, again, in minus out, plus v1 squared minus v2 squared all over 2, kinetic energy in minus kinetic energy out, plus the potential energy in, gz1 minus z2, potential energy out. That whole sum, add all the ins, subtract all the outs. If it's flowing steady, that equals 0. Okay. Now, so what are some situations where I've got steady flow? Well, there are some common devices. Let me make sure I'm not getting a glare here. Izzy, you're just fine. So, there are a number of steady flow devices we might observe. And you're going to see these throughout your text. We're going to see these a little bit in class. You're going to see these in the homework problems. I'm not going to go in depth. There's in our text, section 5.4 talks in depth about these, does a better job than I'm going to. I'm going to give you the crash course. We're going to talk about a few of these. Again, just try to give us some survival information on these. So if we talk about a nozzle, I'm still on the green screen there. Yeah, just barely, all right. So if we talk about a nozzle, so if we talk about some common steady flow devices. Now again, be sure to read through the section in your text that talks about these. It's going to do a better job than I am, but let's talk about the basics here. So you can have a nozzle. A nozzle is a typical device with one inlet and one outlet. The purpose of a nozzle is to increase the speed or velocity of the fluid. So the way we would draw this on a diagram, we draw the cross section of it. So it's going from a smaller inlet to a smaller outlet. Now if we look at the conservation of mass, it's going from a larger inlet to a smaller outlet. So if you look at the conservation of mass on this, that says that the m dot at the inlet, we'll call 1, is equal to the m dot at the outlet, assuming this thing's flowing steady. And we said these are all steady flowing devices. Otherwise, in minus out equals change. If it's flowing steady, the change is 0, so the in equals the out. And so what that means then is, remember how we find mass flow rates? Well, we said there's a number of ways, but one of them is you can take the density at 1 times the cross-sectional area at 1 times the speed at 1. That's the mass flow rate coming in, is equal to the density at 2, the area at 2, and the speed at 2. So notice what happens when the area is bigger on this side than it is on that side. Right? For nozzles, A1 is going to be greater than A2, and that's the reason we draw it. We draw it basically with a larger cross-section at the inlet and a smaller cross-section at the outlet. So if A1 is larger than A2, unless you have a noticeable change in the density, the speed at 2 is going to be larger. If the area decreases, right, the speed most likely is going to increase. The density may also change. The density might also increase as well. If I'm dealing with a liquid, it really doesn't change much. If I'm dealing with a gas, the density may also change. If I hit supersonic speeds, then a lot of very interesting things happen. We don't talk about those in fluid mechanics until the end of the semester, so if at all. So let's not worry about supersonic flow. The latter chapters in your text actually does talk about supersonic flow. We're not going to get there. Just briefly mention it a little bit in chapter 6, and that's about it. So, nozzle decreases the area, most likely thereby increases the speed of the fluid. That's going to be the purpose of a nozzle. The purpose of a diffuser is kind of the reverse of a nozzle, but really the purpose of a diffuser is to increase the pressure. Right? So it increases the pressure. And the way it increases the pressure is by decreasing the speed. So it's kind of the reverse nozzle. A diffuser is this device where you've got flow, mass, fluid coming in, you've got mass going out. Right? And what happens is A1 is smaller than A2. It goes from a smaller area to a larger area. And what happens is, as it does this, the fluid slows down, and more high-speed fluid's trying to get in here, and it's trying to push this low-speed fluid as it slows down coming in. This fluid tries to push it out of its way, and as it does, it's applying an increased pressure. So as the fluid slows down, that kinetic energy has to do something. Well, what happens is that kinetic energy turns into essentially pressure, which shows up then essentially in the enthalpy term. Okay? Alright, so what do we do after that? Couple of things to mention. Probably, I think you can see this, right? Yeah, I know it's kind of, there we are. So probably no work being done unless there's an electrical device of some kind. Most of these devices we're going to talk about, there's probably no major change in potential energy, but you will have a kinetic energy term in these. There will be a lot of devices we will probably neglect the kinetic energy between the inlet and the outlet. This is one device where that's the purpose of these devices, is to change the kinetic energy from the inlet to the outlet. So this is going to be L11, we'll say, and this is going to be page 1. All right, so let's set this aside. Okay, so let's talk about compressors and turbines. So for us, and I've had people in my class before that work for the there's an Air Force base near us. They work in the Air Force, or they work as mechanics on airplanes, and they'll tell me things. Well, a nozzle is actually a compressor. Well, maybe in their nomenclature. For us, a compressor, we're going to go a lot more generic than that, and a compressor is going to be any device that adds work to the fluid stream. All right, so it's going to add energy directly, mechanical energy directly to the fluid. So this definitely requires a work input. And got some diagrams here. I've just pulled these off of Google. You can go Google search compressors, and you'll see. Again, you've got some kind of a. They're saying you've got a drive shaft here, so some kind of spinning shaft causes these blades to spin, and as those blades spin, it pushes the fluid out against the wall, causes an increase in pressure, and that pushes that fluid out. So here, this one is basically pulling fluid in. You got this fan disc that pulls the fluid in and pushes it out through a discharge by some kind of a rotating drive shaft. That's kind of what we would call a turbo configuration of a compressor. This text likes to draw piston cylinder compressors. I don't really care for that. There's some technical reasons for that. Here's how I draw a compressor. So I draw something kind of looks like a nozzle, but instead of the fluid just moving through, I draw the fluid moving in kind of the larger end of the barrel and getting squeezed down and moving out of the kind of the more narrow end. So as the fluid moves through, it gets squeezed down with some kind of a rotating shaft. So we draw out here just a little bit of a rotating shaft and draw a power input. Okay. Probably no major potential energy change. That's a pretty common thing. We're normally going to assume the potential energy change is negligible, but a compressor definitely requires a power input or a work input. Examples of compressors: fans, pumps. Pump is a special type of compressor that compresses liquid, but liquid doesn't compress, so really what you do is you just increase the pressure. But fans, pumps, and then just a generic compressor. We don't necessarily have to worry about what kind of compressor it is and how it's compressing the fluid or what it's really doing to the fluid. We just need to know, for our purposes, this is a device that puts power in, and that increases the energy from the inlet to the outlet of the fluid. How that manifests itself, whether it's a pressure increase, a temperature increase, or both, that will be given properties to tell us that. Okay. A turbine, or a turbine. I say turbine. You could say turbine. That's perfectly fine. I like to say turbine. Excuse me. So turbine, this is a device that's kind of the reverse of a compressor. This is a device that extracts. This extracts power from the fluid stream. Okay, and you can see I've paraphrased. This is a paraphrase from the textbook, and this is a paraphrase of my slides, so go back and read the text so you get the original version. This is the dumbed down, stripped down version, so be careful there. With both a turbine and a compressor, you may have a change in kinetic energy, as opposed to these guys where you will have, guaranteed you have a change in kinetic energy in these devices. You may or may not have a change in kinetic energy with a turbine. Okay, probably negligible. Again, I draw the reverse of what I draw for a compressor. Probably negligible potential energy change, but you might have a kinetic energy change. And again, this is a device that's going to extract power. How does it do that? Well, you have fluid coming in, kind of a narrow point, and then what happens in most turbines is you've got a bunch of fan blades in here. You can't see this image probably very well, but if you go look, just go do a Google or image search, whatever search engine you like is fine. Do an image search of a turbine and a steam turbine and see what you see. It's similar to a wind turbine, where when wind blows through a wind turbine, it causes those fan blades to spin. That turns a generator, and that's how we get electricity out. Similar thing here. This is a cross-section of a turbine in a steam power plant. High pressure steam comes in, that causes these blades to spin. We hook up to a shaft, an electrical generator, and that gives us electricity. Next video.